Good morning. This is a continuation of our lecture on integer algorithms, integer representation and algorithms. So one of the algorithms we can discuss is an addition algorithm. Consider the problem of adding two integers in binary notation. A procedure to perform addition can be based on the usual method for adding numbers with pencil and paper. The method proceeds by adding pairs of binary digits together with carries when they occur to compute the sum of two integers. This procedure will now be specified in detail. To add in A and B, add their rightmost digits, which we have given a subscript of 0, where S sub 0 is the rightmost bit in the binary expansion of A plus B, and C sub 0 is the carry, which is either a 0 or 1. Then add the next pair of bits and the carry, A1 plus B1 plus C sub 0 is equal to C1 times 2 plus S sub 1, where S sub 1 is the next bit from the right in the binary expansion of A plus B and C sub 1 in the carry. Continue this process, adding the corresponding bits in the two binary expansions and the carry to determine the next bit from the right in the binary expansion of A plus B. At the last stage, add A subscript n minus 1, B subscript n minus 1, and C subscript n minus t to obtain C n minus 1 times 2 plus S n minus 1, where S stands for the sum. The leading bit of the sum is S subscript n, and it's equal to the n minus 1 carry. This procedure produces the binary expansion of the sum, namely A plus B is equal to the nth bit of the sum down to the 0th bit of the sum. So here's an example. Add 1110 base 2 to 1011. So I get 0 plus 1 is 0 times 2 plus 1. So the carry out is 0 and the sum is 1. A plus 1, A1 plus B1 plus C0 is 1 plus 1 plus 0 is 1 times 2 plus 0. C1 is equal to 1 and S1 is equal to 0. A2 plus B2 plus C1, 1 plus 0 plus 1 is 1 times 2 plus 0, and in the output is the carry is 1 and the sum is 0. A plus 3 plus A3 plus B3 plus C2 is 111. Add them all together. 1 times 2 plus 1 is the carry out is 1 and the sum is 1. So we can see this if we align them up. We have 3 carries, and when we get all done, we have a sum that's 11001, which we convert first to hex, 19 hex, and then to base 10, 25. Then we use our ordinary decimal arithmetic to take a 14, which is our 1110, and 11, 1011, and add it up, and we check. So we've written here an algorithm for addition to the integers, and you can inspect it at your leisure. And example 9, the conclusion of example 9 is this is an O of n algorithm. It has time complexity O of n. That means it has linear time complexity. Here we have a multiplication, and we can use multiplication in the same way, binary multiplication in the same way as we do decimal multiplication. And so I have an example here in figure 2. And so what I'm going to multiply is 5 or 6 times 5. So what I do is I have a 1 in the least significant PL, and this is very nice in binary because 1 copies. So I copy the 110 directly down here. Then 0 makes the next product all zeros. So I take these 3 digits, since they're multiplied by zeros, they're going to all be zeros. So I move that and align it with the deal. And then I take another 110, and I put it in its place. And then I add the rightmost column to be 0, the next rightmost column to be 1, the next most right column to be 1, and we have 1s out here at product. So what we have is 6 times 5 is 30 in decimal, and we hope that 1110, which we've translated to 1 easy base 16, is also equal to 60, and it is. I mean, it is equal to 30. Example 11 says that multiplication is an O of n squared algorithm. Here we have an algorithm for division and mod, and what we basically do to get the division is we repeatedly subtract, and every time we subtract we increment the value of q, the quotient, until until our remainder is smaller than our divisor. And we use a similar technique for finding the remainder, the modular. So here we have an algorithm for modular exponentiation, and what we're going to do with this modular exponentiation is we're going to take the exponent and give the binary representation of the exponent. And here what we can see is we have 3 to the 11th. And so the binary exponentiation of this is 3 to the 8th times 3 to squared times 3 to the 1. And what we're going to do is we're going to take our 3 and double it every time, so that we have 3 to the 1 power first time around, 3 to the 2nd power the second time around, 3 to the 4th power the 3rd time around, and 3 to the 8th power the next time around. So by continually doubling our powers, we can very rapidly get at our final result of 177,147. So example 11 is an illustration of how you can take 3 to the 644 power mod 645 and find it. And so our answer is 36. And that concludes our lecture.